Hello and welcome to this session. In today's session, we'll now start with auto transformers. So, unlike the conventional transformers, auto transformers do not make use of electrically isolated windings. In case of auto transformers, the two windings that we'll be using will be electrically coupled. And where do we use auto transformers is specifically in those case of applications, in those applications where the requirement of voltage to be up or to be down is very low. Say, for example, we want to up the voltage from 210 to 220, or from we want to decrease the voltage from 240 to 230. Fine. So, or it can be in kilovolts. So we can say, for example, we want to decrease the voltage from 15 kilovolts to 14.8 kilovolts, something like that, or we are increasing the voltage by a small magnitude. And this, in those cases, we do not make use of conventional transformers in order to reduce the cost and to also to make sure that the number of the winding actually used is reduced, the coil actually used is reduced. We make use of auto transformers. So what are auto transformers? As you can see here, from a conventional transformer, we are designing an auto transformer. A conventional transformer has a primary winding and a secondary winding. They are electrically isolated from each other, but using those two windings in series in an additive manner, you can get a step-up auto transformer, or using those two windings in series in a subtractive manner, you can get a step-down transformer, step-down auto transformer. So by just combining the primary and the secondary winding in series, here specifically the secondary winding and the primary winding will have they need to have specific type of the number of turns of the coils will be of specific magnitude. Fine. So we'll actually be seeing that. So if you look at the diagram, you have various parameters. You have VSC, VC. So what is VSC and VC? VSC here refers to the voltage across which winding, that is now series winding. We'll now be calling, instead of calling them primary and secondary winding, we'll be calling them as common winding and series winding. Common winding is that part of this transformer which is actually common to both the low voltage side as well as the high voltage side. So voltage across the common winding is VC. Voltage across that portion of the auto transformer is actually only available on one side of the transformer, that is the high voltage side only, will be referred to as the series winding. So you have VSC and VC, voltage across series winding. And voltage across common winding. And you also have the currents ISC and IC, the currents that are flowing through these windings. NSC and NC. NSC is the number of turns of the series winding, NC is the number of turns of the common winding. So as if these two windings were separate, we would know that VSC or VC divided by VSC is equal to NC divided by NSC. So this equation is actually valid for the auto transformer as well. Similarly, IC divided by ISC is equal to NSE divided by NC. We know these two equations from the conventional transformer, and they are also valid for the auto transformer. But instead of finding the voltage and current in terms of IC, ISC, we want to find out the voltage on the terminals. That is, we want to find out the relationship between VL and VH, and we want to find out the relationship between IL and IH, where VL is the voltage on the terminals of the low voltage side, VH is the voltage on the terminals of the high voltage side, IL and IH similarly, they are the currents in the low voltage and the high voltage winding. We want to find out basically VL divided by VH. So what will this be equal to? Now, from this equation, from these two equations, we know VC divided by VC is equal to uh, NC divided VC by VSC is equal to NC divided by NSC. Uh, Now, from this we also know VL is equal to, from the diagram, VL is equal to VC and VH is equal to VC plus VSC. Therefore, VH is equal to VC. This I want. This is VC is equal to NC divided by NC into VSC. So instead of VC, I will be writing now VC be same. VSC we know VSC from this equation, from equation number 1, VSC is equal to NSC divided by NC into VC. Fine. Uh, so VH is equal to VC plus NSC divided by NC into VC. Therefore, VH is equal to VC common. We have 1 plus NSE divided by NC, which implies VH divided by VC. What is VH equal to VC equal to? That's equal to VL. So VH divided by VL is equal to NC plus NSC divided by NC. So this is VH by VL, or you can write VL by VH is equal to NC divided by NC plus NSC. So this is VH by VL equation. Fine. Or you can say VL divided by VH is equal to NC divided by NC plus NSC. Similarly, we know diagram. You can also find the current equations. You know that IH is equal to the current that is flowing in the series winding ISC, while as IL is equal to ISC plus IC. Fine. We already know the relationship between ISC, IC, and ISC. Therefore, IL is equal to, instead of ISC is same, plus instead of IC, I'll be writing IC is equal to, from this equation, IC is equal to NSC divided by NC times ISC. So taking out ISC common, so IL is equal to ISC 1 plus NSE divided by NC. ISC we know is already equal to IH, therefore IL is equal to 1 by H NC plus NSC divided by NC. Fine. So VL by VH, you can say this equation A, and IL divided by IH. This is equation number B. So VL divided by VH is equal to NC divided by NC plus NSC, and IL divided by IH is equal to NC plus NSC divided by NC. So this is the voltage and current equation of an auto transformer. So this is valid for both the step up as well as the step down auto transformer. Now, one more advantage of using an auto transformer is the power rating advantage. So we'll be discussing now the power rating advantage of the auto transformer. So now we'll be discussing the apparent power rating advantage of an auto transformer. So you have the equations that we just found out. VL divided by VH is equal to NC divided by NC plus NSC, and IL divided by IH is equal to NC plus NSC divided by N. So this is what we just derived, the power and the voltage and current equations of an auto transformer. Now let's look at the input power of this auto transformer. The input power of the auto transformer is VL IL, and the output power of this transformer is VH IH. So you can, if you substitute these equations, you will see that the input power will be equal to the output power of this transformer, and let that be equal to SAT. Fine. So the output power rating of this transformer is given. This is the apparent power rating of this auto transformer is given to us by SAT. That's simply VLIL or VHIH. Now let us look at the rating of the winding of the transformer. In case of a conventional transformer, the input power rating will be, say for example, if it is P, the rating of the windings will also be equal to P. There will be no difference there. Now let's see what happens in case of an auto transformer. Now, if you look at the winding rating, SW, it is equal to, you can say it is VC IC, or you have VSC ISE. Now we know here that VC is equal to VL and IC is equal to IL plus IC is equal to IL minus IH. So therefore, the apparent power rating of the windings of the transformer is VL IL minus VL IH. Now substituting this equation here, we are actually substituting for IH. So SW will be equal to VL IL minus, this is the rating of the winding, the power rating of the winding, VL, instead of IH you have NC divided by NC plus NSC times IL. Fine. So that means VL IL minus VL IL times NC divided by NC plus NSC. What is VLIL? VLIL is the rating of the power rating of the auto transformer. So we have taking this VLIL common from here. VLIL is SAT actually. This is 1 minus NC divided by NC plus NSC. So SW divided by SAT is equal to NC plus NSC minus NC, that's actually NSC divided by NC plus NSE. So SW is equal to NSE divided by NC plus NSC times SAT. Now in case of a conventional transformer, the power rating of the winding will be equal to the power rating of the transformer itself, not the auto transformer. Fine. So this is for a conventional transformer. But for an auto transformer, the power rating of the winding is equal to NSC divided by NC plus NSC. So this ratio NSC divided by NC plus NSC will be less than 1. So that means it's actually a fraction of SAT. So if SAT, say for example 1000, so it will be definitely, it can be 900, 800 depending upon whatever is the value of NSC and NC. So most likely NC is going to be much higher than NSC. The common winding is much more number of turns. So say for example, we have NC equal to 100, NSC is equal to 10. That means this is 10 divided by 110 into SAT. That means actually 1 by 11th of SAT. Fine. So the power rating of the winding is 1 by 11th of the power rating of the auto transformer. That means the winding design will be, we do not require, if the auto transformer rating is 100 kVA, the winding rating will be only uh, say for example 10 kVA or 20 kVA or 30 kVA, it will be something like that. So in case of an auto transformer, the winding rating, the power rating of the winding is much less. So we do not need a large winding, or we do not need a winding with sufficient diameter to have that is actually going to be. So what is this going to mean for the auto transformer? This simply means that if the winding rating is 1 by 10th of the transformer rating, the windings required will be less. That means the size of the auto transformer will be less, the size of the winding will be less. So therefore, auto transformer has the advantage over a conventional transformer. That means its size will be less, its power rating or the winding requirement is actually less. So this is another advantage of using an auto transformer. The power rating or the winding is much less, so we can design the same auto transformer will be cheaper, and the size will be less. So it is going to be cheaper also on two accounts, because it is also going to consume lesser winding, as well as the power requirements will be less for the winding. So this is an advantage with an auto transformer over a conventional transformer. Uh, so here I'm also going to show you a solved numerical. So go through this numerical, it's solved, and it's pretty easy to understand. Also from this numerical, you can basically understand the uh, advantage of using an auto transformer. So fine. So you have an auto transformer. We use auto transformers where voltage stepping up or stepping down requirements is less. We do not need to step up or step down by a greater magnitude. The voltage and current equations of the auto transformer have been given. We derived that. Also, we found out the power rating advantage of using an auto transformer. And we also have one solved numerical that you go through and see how the auto transformer is much more useful, much more offers better advantage as compared to a conventional transformer.